All right, ready to dive into some cutting-edge AI.
Let's do it.
Okay, so we got this paper on DynaSaur.
Yeah, DynaSaur. It's a new LLM agent framework. It's causing quite a stir.
Lots of buzz, for sure. And for good reason. It can create and execute tasks dynamically.
Way beyond the usual pre-programmed stuff.
Right, like it breaks free from those limitations. A big deal for anyone in AI.
Absolutely. Especially in academia research.
Oh, yeah. And in tech in general.
I mean, anyone who's worked with AI agents knows the problem. Predefined actions.
Let's hit a wall.
They do.
Yeah.
Complex environments, forget it.
It's like they get stuck.
Yeah.
No flexibility.
Exactly. You give them a fixed set of actions.
And that's all they've got. Like a toolbox.
Yeah, toolbox with just a hammer and a screwdriver.
Exactly.
You can do some basic stuff, but anything complicated.
No way.
Nope. You need specialized tools for that.
And that's what DynaSaur is all about.
That's it. It lets the agent make its own tools on the fly.
Really?
Yeah, it interacts with the environment, and it actually generates programs.
Programs.
Programs in a general purpose programming language.
Wow.
Yeah. So it's not just picking from a list of actions.
That's writing code.
It's writing code.
Yeah.
To do whatever it needs to do.
So instead of fixed actions.
It's got this whole dynamic range. It can adapt.
That's incredible. So what happens to those generated actions?
It keeps them for future use. Think of it like
a skill set.
Exactly. It's building a dynamic skill set. So it uses this.
What language? Python.
Could be Python, yeah. Any general purpose language, really. It's like translating.
Translating what?
Translating its understanding of the environment into instructions it can actually run.
And then it stores those instructions.
It stores them,
Yeah.
indexes them. So the next time it needs to do something similar.
It's got a library to pull from.
Exactly. So the more it interacts.
The bigger the library gets.
Right.
And the more adaptable it becomes.
Right. Compared to those agents with predefined actions.
Night and day.
Totally. And the paper shows this. They tested it on the GAIA benchmark.
The GAIA benchmark.
Yeah. It's a way to measure how well these agents perform. And DynaSaur.
I bet it blew the others out of the water.
It did. Big time. Flexibility, performance, just way ahead. And it can even recover.
Recover from what?
From situations where other methods would just fail. You know, if the predefined actions
aren't enough.
Exactly. DynaSaur can just create a new action specifically for that situation.
Wow. So it's like it's got this problem-solving mechanism built in.
Exactly. Something new comes up that figures out a way to deal with it.
That's incredible. What are the real-world implications of this?
Oh, man. So many. Think robotics.
Robotics.
Imagine a robot that can learn new tasks without needing to be reprogrammed.
No way.
That's the kind of flexibility DynaSaur offers.
Okay. So we've got the high-level view. Can we get a little more technical?
Sure. So the architecture of DynaSaur.
Yeah, break it down for us.
Okay. So you've got the environment, the world the agent interacts with.
Got it.
Then there's the agent itself, which is made up of an LLM and an action library.
The action library is where those dynamically generated actions live, right?
That's it.
But how does the agent decide what code to generate? I mean, for a specific task.
That's the magic part. So the agent takes an observation of the environment.
Like a snapshot.
Kind of. It could be text describing the scene, or even sensory input, like images.
Okay.
And the LLM processes that observation. And using its knowledge of the programming language, it generates a program.
To achieve a goal.
Right. A specific goal within that environment.
So the LLM is like a programmer, translating the goal into instructions.
Exactly. And the programming language matters. DynaSaur uses a general purpose language.
Why is that important?
It means a much wider range of actions compared to a domain-specific language.
More flexibility.
Way more flexibility. Right. That's what gives DynaSaur its edge.
This is fascinating stuff. But I gotta ask, how do you even train the LLM to do this?
Good question. So it needs to understand the structure of the programming language.
The syntax.
Right, the syntax. And how code actually affects the environment. So the training involves a massive data set of code.
Like a code library.
Yeah. And each piece of code is paired with descriptions of what it does.
So the LLM learns to map language to code.
Exactly. You're teaching it to think like a programmer, to understand that a certain sequence of code
will have a specific outcome.
Right. It's a complex process, of course, getting the LLM to generate code that's correct and efficient, but
The results speak for themselves.
they do. DynaSaur is showing us what's possible.
It is. But what about safety? I mean, with the AI generating code on the fly?
That's a huge consideration and an active area of research. One approach is formal verification.
To check the code for errors.
Exactly,
Yeah.
or vulnerabilities. Another approach is sandboxing.
Tinboxing.
Yeah, you execute the code in a restricted environment.
So it can't do any damage.
Right, it limits its access to sensitive resources.
Makes sense.
And as the technology matures, I think we'll see even more sophisticated safety measures.
So it's about finding that balance.
Exactly, between flexibility and safety.
Because with any powerful technology,
There are risks.
absolutely. But the potential benefits of DynaSaur are huge, especially its adaptability.
Oh, yeah. It can learn and adapt in complex environments. That's what makes it so exciting.
Let's talk more about those benefits. The paper mentions some impressive results on that GAIA benchmark.
Right, the GAIA benchmark. It's a really challenging suite of tasks.
What makes it so challenging?
Well, it's all about interactive environments. The agent has to interact with a simulated world through text.
Okay.
And it has to solve problems, achieve specific goals. It's a really comprehensive test.
So it's not just about writing code.
No, it's about understanding language, reasoning about the environment,
Right.
and taking action.
It's a test of intelligence.
Exactly. And DynaSaur.
I'm guessing it aced it.
It did. It consistently outperforms other methods. It's really remarkable.
Can you give us some examples of where DynaSaur really shines?
Sure. One area is complex planning and problem solving. Like imagine the agent has to collect objects. Okay.
But they're scattered across a virtual environment, and there are obstacles in the way. And it has limited carrying capacity.
Oh, wow. That sounds tricky.
It is. For traditional LLM agents, this would be a nightmare. They'd probably get stuck.
Because they rely on those predefined actions.
Exactly. But DynaSaur, it analyzes the situation, generates a program, navigates around the obstacles, prioritizes the objects.
Then comes up with a solution.
It adapts its strategy on the fly based on what it encounters.
It's like it's thinking strategically.
It is. It's planning ahead, anticipating challenges.
That's amazing. And this ability to plan and adapt makes it perfect for real-world applications.
Absolutely.
Yeah.
Where the environment is unpredictable. And you need an agent that can think on its feet.
Like what?
Oh, think robotics, autonomous driving, even personalized healthcare. Anywhere where adaptability is key.
Wow. This is incredible stuff. But I'm also curious about its limitations.
Sure. So one thing is its performance is still tied to the quality of the LLM.
And the training data. Right. If the LLM isn't well trained. Or the data is biased, incomplete. The generated programs might not be so great.
So even though it's a leap forward,
It's not perfect. There's still work to do in improving the accuracy, efficiency, safety of program synthesis.
and what about the computational cost? Generating code on the fly must be expensive.
Yeah, that's a valid concern. It can be computationally intensive, but there are strategies for optimization.
Like what?
Well, using more efficient LLMs, for one, caching previously generated programs.
So you don't have to generate them again.
Exactly, and parallel processing techniques, anything to make the process more streamlined.
Makes sense. So it's about finding that sweet spot.
It is. But even with these challenges, DynaSaur is a major step forward for intelligent AI agents.
I agree. It's a game changer.
Yeah.
And it shows the incredible ingenuity of the AI research community.
It does, and it gives us a glimpse into the future of AI.
A future where AI can truly adapt and learn.
Exactly.
This has been an amazing discussion. Thank you so much.
My pleasure. Yeah, it really is a game changer. And when you look at how it uses that code, it gets even more interesting.
Okay, so it can write programs,
Yeah.
but how does it actually use them to interact with the environment, solve problems?
All right, picture this. The AI agent is in a new environment, say a virtual world.
Okay, a virtual world.
And it's given a task.
Okay, a task.
The agent observes the environment, collects information about the surroundings, the task itself.
Gotta.
That observation is fed into the LLM, which then uses its knowledge of the programming language to generate a program.
And that program is like?
A set of instructions guiding the agent's actions.
Like a plan.
Exactly, a plan of action tailored to that specific situation.
And it can change the plan.
Oh, absolutely. As it interacts with the environment, gets more information, it can adapt.
So it's not just generating code, it's using the code to act intelligently.
Right. Navigating the environment, manipulating things. And that's where action accumulation comes in.
Action accumulation?
Yeah, remember how it stores those generated actions?
Right, for future use.
So let's say the agent creates a program to get around an obstacle.
Okay.
It stores that program along with the context in its action library.
Got it.
Then later, it encounters a similar obstacle in a different situation.
And it can just pull out that old program.
Exactly. Reuse it. Save time and resources. It's like,
Building up a library of skills.
yes, learning from experience, becoming more efficient.
That's fascinating. It's like meta learning.
You got it. It's not just learning to solve tasks, it's learning how to learn.
Wow. Okay, so now I'm even more curious about this general purpose programming language thing. Why is that so important?
It's all about flexibility and expressiveness.
Okay.
Using something like Python, it means the agent isn't limited to those predefined actions.
Right.
It can express any computational task that can be written in that language.
It's like giving the AI a more powerful set of tools.
Exactly. It can create its own solutions
Yeah.
using the full power of the language.
And that's essential for adaptability.
It is. When it encounters something new, something unexpected, it can figure it out.
But does using a general purpose language make development harder? I mean, debugging and all that.
It does add complexity, but honestly, the benefits outweigh the challenges. Think about it. Python, for example, is widely used.
Right.
So there are tons of tools, libraries, debugging resources. Developers can use all that to analyze the code, catch errors.
So you're tapping into the whole programming community.
Exactly. And what about the community's reaction to DynaSaur? Well, let me tell you.
They love it.
There's a ton of excitement, lots of discussion. People see it as a major step forward for building more robust, adaptable AI.
What about specific applications? Where's the most interest?
Robotics is huge. Imagine robots that can learn new tasks on their own, adapt to new environments, collaborate with humans more naturally.
Wow. That's a whole different level of robotics.
It is. DynaSaur could make that possible. By dynamically generating and executing programs, it's a game changer for robotics.
It really is. It feels like DynaSaur is more than just a technological advancement.
It is. It's a shift in how we think about AI.
Right. It's not just about rules anymore.
It's about something much more dynamic.
So we've been looking at DynaSaur from a programming perspective, but what about the math behind it?
Ah, the mathematical foundations. Fascinating stuff.
What are the key concepts that make all this possible?
Well, at its core, DynaSaur relies on probability and statistics,
Oh, okay.
especially in how it trains and uses the LLM. One key concept is Bayesian inference.
Literally, man, friends.
It's a way for the LLM to update its beliefs based on new evidence. In this case, the evidence is the observation of the environment and the desired goal.
So it's not just spitting out code randomly, it's making informed decisions.
Exactly. It's using Bayesian inference to estimate the probability of different programs working, given what it observes.
That's like it's reasoning, figuring out the best course of action.
Exactly. And another important concept is Markov decision processes, or MDPs. They provide a framework for decision-making in situations where things are partly random and partly under the agent's control.
So it's like acknowledging that the AI can't control everything.
Right. There's uncertainty. The MDP helps DynaSaur reason about the consequences of different actions.
While taking into account that randomness.
Exactly. It's planning under uncertainty, which is crucial for real-world applications.
This is all so complex, but it's also incredibly elegant. It's like computer science, math, cognitive science, all coming together.
A beautiful blend of disciplines. And that mathematical foundation is what allows DynaSaur to go beyond simple pattern recognition. It can actually reason, solve problems.
Like a human.
In a way, yes.
Okay, so how does this mathematical foundation affect scalability? Can DynaSaur handle more complex tasks, more complex environments?
That's the big question, and researchers are working on it. The computational demands can increase rapidly as tasks get more complex.
So those optimization strategies we talked about are important.
Crucial. Caching, using efficient LLMs, parallel processing. It's all about managing that complexity.
Without losing the flexibility that makes DynaSaur so powerful.
Exactly. It's a delicate balance. But the progress is undeniable. LLM-based program synthesis is advancing at an incredible pace.
It feels like we're at a turning point.
It does. And for our listeners, especially those in academia, research, tech.
Yeah, what should they be thinking about as this technology evolves?
Well, DynaSaur shows us the power of dynamic action generation. It's a fundamental shift. From rigid AI to systems that can learn, adapt, solve problems creatively.
That's a big deal. For robotics, personalized medicine, so many fields.
It is, and it's a call to action for researchers to find new ways to train LLMs, to improve program synthesis techniques, and to address the ethical implications.
A societal impact.
Exactly. We need to guide this technology responsibly.
Absolutely. The future of AI is in our hands. And with frameworks like DynaSaur, we have incredible tools to shape that future.
Powerful tools.
This has been an incredible deep dive into DynaSaur. We've covered so much.
Yeah.
The technical details, the math, the potential.
It's been a pleasure exploring it with you. The research is fascinating.
It is. And for our listeners, we encourage you to check out the DynaSaur paper. Dive deeper. Join the conversation. The future of AI is happening now.
It is, and it's full of possibilities.
Yeah, it feels like a whole new frontier. AI that can think on its feet.
It's a game changer for sure.
So we've been talking about DynaSaur mostly in terms of programming, but I'm curious about the math behind it all. What are the core mathematical concepts that make this level of program synthesis possible? You know, the dynamic action generation and all that.
Yes, the mathematical underpinnings. It's a fascinating area. At its heart, DynaSaur relies heavily on probability and statistics.
Probability and statistics.
Exactly, especially in how it trains and utilizes the LLM. One of the key concepts here is Bayesian inference.
Bayesian inference. Now, that rings a bell. But could you remind us?
Of course. Think of it as a way for the LLM to update its beliefs about the world based on new evidence it receives.
So in this case, the evidence would be?
The observation of the environment and the goal it's trying to achieve.
So it's not just randomly generating code, it's actually making informed decisions based on what it knows.
Precisely. The LLM uses Bayesian inference to figure out the probability of different programs actually working, given the current situation.
It's like it's reasoning, trying to figure out the most likely path to success.
Exactly. It's like a detective piecing together clues. And another important concept is Markov decision processes.
Markov decision processes.
MDPs for short. They provide a framework for making decisions in situations where outcomes are partly random and partly under the control of the agent, meaning the AI doesn't have complete control over everything.
Right, there's always some uncertainty.
Exactly. And the MDP helps DynaSaur reason about the consequences of its actions, taking into account that randomness.
It's planning for the unexpected.
Precisely. It's planning under uncertainty. And that's crucial for real-world scenarios.
It's amazing how all these different fields are coming together. Computer science, math, cognitive science.
It's a beautiful convergence. And that mathematical foundation is what allows DynaSaur to go beyond just pattern recognition. It can actually reason, solve problems in a way that's closer to human cognition.
It's pretty mind-blowing. But how does all this math affect scalability? Can DynaSaur keep up as tasks and environments get more complex?
That's a great question and a key area of research. As you can imagine, the computational demands can grow pretty quickly as things get more complex.
I can imagine.
And that's where those optimization strategies we talked about come in, using efficient LLMs, caching, parallel processing. All those things become crucial for managing that complexity.
Right, without sacrificing the flexibility that makes DynaSaur so powerful.
Exactly. It's a balancing act. But the progress we're seeing in this field is truly exciting.
It is. It feels like we're just scratching the surface of what's possible.
I agree. And for our listeners out there, especially those in academia, research, tech, it's an exciting time to be involved in this field.
Absolutely. So what are some key takeaways for them as this technology continues to develop?
Well, first and foremost, DynaSaur really highlights the power of dynamic action generation, this idea of moving away from rigid, pre-programmed AI and towards systems that can learn, adapt, solve problems in creative ways. It has huge implications for robotics, for medicine, for so many fields.
It's a paradigm shift.
It is, and it also presents new challenges. Researchers need to find better ways to train LLMs, improve those program synthesis techniques, and we can't forget about the ethical implications, the potential societal impact.
We need to guide this technology responsibly.
Absolutely. The future of AI is something we're all shaping. And with frameworks like DynaSaur, we have the tools to make it a positive future.
It's been an incredible deep dive. We've covered a lot of ground. The technical details, the math, the potential. I feel like I've learned so much.
Me too. It's been a fascinating discussion.
And for our listeners, I encourage you to check out the DynaSaur paper. Dig in, explore. This is the future of AI unfolding.
Join the conversation. Be a part of it.
Thank you for joining us on this episode of The Deep Dive. We'll see you next time.
Until then, keep exploring, keep learning, and keep pushing the boundaries of what's possible.